Okay, hello everybody. Let's start the session for this afternoon. So this is my pleasure to introduce Peter Gartner from Typhoon HIL. So Peter has been within Typhoon HIL for 7 years. He's currently a senior modeling engineer, and he's dealing with development and maintenance of high-fidelity electrical machine and power electronics converter model for real-time simulation. So his presentation today will be about our hardware in the loop, as you may guess it. So thank you very much for joining. And I think now, Peter, you can start and share your screen.
Okay, thank you for the nice introduction. Just let me know when you see the screen.
Yeah, we can see.
Okay, great, thank you. So
we can clearly hear you, that's okay.
Okay, great. So yeah, welcome to a better way to design and test motor drive simulation. So first, I'd just like to thank again the PowerSys and JMAG for having us again. And yeah, last time it was really fun, so hopefully it will be fun this time around as well. So yeah, my name is Peter, and I'll do this presentation. Well, let's start with the agenda for today. So first, we'll briefly talk about model-based control software development and testing. After that, we'll focus on the integration between JMAG-RT and Typhoon HIL. Finally, then we'll go through a demonstration of a PMSM drive on Typhoon HIL. So we'll show how to build a power stage in Typhoon, how to import the JMAG-RT generated machine model. We'll run a simulation, do a couple of scenarios like fault injection, some torque steps, and we'll show an example of an automated test. And we'll leave some time at the end for the Q&A. So a little bit about the motivation for all of this. So if we take a look, for example, at the electric vehicle market, we can notice a trend of increasing performance requirements. So we want higher efficiency systems, higher power density, increased reliability, safety, and fault tolerance. And at the same time, there is always a pressure to shorten the time to market our products. So all the while, electric vehicles are becoming more and more complex systems. So they can comprise from one motor inverter all the way up to four motor inverters. On top of that, still there are design requirements for onboard chargers, for stationary chargers, and for vehicle-to-grid interaction. So again, in terms of efficiency, interoperability, grid code compliance, and etc. So with all of this, we can see that the control software complexity in electric vehicles is exploding. So we need to start thinking about ways to deal with this complexity, and we need to come up with some viable solution for it. So one approach that has proven useful is model-based design and testing. So there are reports that show that utilizing model-based control software design and testing practices can help us achieve 30% better schedule performance. So we release products within the given timeline. It can help us reach 70% reduction in the number of defects. It can help us put out up to 40% more control code. So it can make smaller teams more efficient. Now, there is a significant obstacle in properly utilizing model-based design and testing practices, And it is, in fact, the lack of integration between design and testing tools. So this then can create inefficiencies. For example, it is not always easy or straightforward to deploy models developed in one environment or in one model-based design tool into the other. And it is this integration between design and testing that we're actually trying to address by working with PowerSys and JMAG. So before we go any further, I'll just say a few words about what is model-based control development and testing in general. So if we think of a typical electric vehicle propulsion system, now how do we start with the control software development? So we typically model the power stage. So for example, the battery, in the inverter and the machine, but then we also model the controller. So the controller model is initially usually simple. It only has a few features, but it still works in a loop with the power stage model. So we call this step model in the loop. So because we have both the model of the power stage and the model of a controller working together. And this is typically performed using offline simulators. Now, the next step, what we can do one better than the model in the loop is, now that we've established a specification or established the power stage model and the initial controller functionality, we can move to what is called software in the loop. So here we generate the controller code, either type it by hand or generated using automatic code generation tools, and that is supposed to be the code that will actually end up on a real controller, on a real ECU. So now we still have two software entities talking to each other, so the power stage model and the controller code. But this time we don't have a model of the controller, we have what is supposed to be at some point the actual control code. And then finally, what we have is the controller hardware in the loop, which we will focus on the most in this presentation. So what this means, what is controller hardware in the loop is it's where the controller hardware is actually in the loop with a real-time simulator of the power stage. So we have a real ECU that's running the actual controller code, and all the analog and digital connections are to the simulator are the same as they would be in a real system. Now, this whole system, the controller plus the HIL, works in such a way that the ECU can tell whether it's controlling the simulator or a real plant. Now, all of this is only one part of the approach. So up to here, we've been talking about the design part. Now, there is another thing, and this is maybe the more important thing. It's the testing. So what all of this steps over here, this whole approach, model-based approach, allows us to do is to leverage test automation infrastructure from early on in the process. So what we want to do is start testing as soon as possible, and we want to also fail those tests as soon as possible and then improve, because when we fail the tests, we actually see where we've made the mistakes. So be it in the specification for some parts of the system or in the performance of the system, etc. So Typhoon HIL testing platform, or Typhoon Test, allows us to use this testing approach throughout the whole process. So from model in the loop, through software in the loop, to finally controller hardware in the loop. Now, of course, if you're more familiar with other testing platforms like NI Test Stand, ETAS Lab Car Automation, or for example, Tracetronic ECU Test. So these are only other examples of test automation frameworks. You can also use this with Typhoon HIL to perform testing automation and deployment of the controller code. So essentially, we see testing as a way to help us deal with the complexity that's in the controllers, basically. So if we use hardware in the loop, testing can become an integral part of the design workflow, and we can utilize testing much earlier, start using it much earlier in the process, even before an actual plant becomes available. Now, for example, we can import the JMAG-RT model and test our drivetrain controller even before the prototype or the physical test bench is available. Now, there's one thing that we didn't mention here, and it's that the motor drive design actually starts with designing a motor, right? So a lot of people use JMAG finite element analysis tools to come up with detailed designs for their propulsion motors. And this highly detailed model can then be converted to a JMAG-RT model that's suitable for system level simulations. Now, this model is, although reduced order, the JMAG-RT model, it's still very high fidelity, and it can be seamlessly imported into model-based software environments such as Typhoon. Now, we use JMAG-RT to generate a high fidelity plant model for system level simulation. So those simulations can be either offline or real time. And since the model is high fidelity, it reflects the behavior of the actual device, of the actual plant that we plan to have in the end. Now, the JMAG-RT models are highly accurate 1D model that have comprehensive motor characteristics extracted from the finite element model. So these models consider nonlinear effects, they consider saturation, they consider space harmonics. So essentially, all the physics that goes into the machine. So both the geometry and the materials used in the sorry, when building the actual machine. So the step from to obtain JMAG-RT models is quite simple, basically. So there are several ways to do it. We can start with, for example, designing our own motor in JMAG Express or JMAG Designer. Another way is to use measurements from a real machine. And also, there's a number of existing design templates or ready-made designs that can be used as a starting point or as a final point, maybe in some cases. And now, the typical JMAG-RT workflow is to create a finite element model using JMAG, then open up the JMAG-RT library manager, import the FEA model into the library manager, specify the settings for the FEA model, create the JMAG-RT model, which ends up basically as a single file that contains all the data relevant for a system level simulation. And then as such, it can be imported directly to model-based software environment. So for example, what we want to get and what we'll show in the demo a little bit later is we want to have a high fidelity plant model running on a real-time simulator. Then we plug into the controller to this system. So then the controller actually doesn't know that it's controlling the simulation instead of the real plant, as we said already. And then we can play around, see what's going on, improve our code, test, and so on. Now, I'm going to switch a little bit to talk about the Typhoon HIL and the workflow there. So what we'll mainly focus on today are these three tools. So the schematic editor, HIL SCADA, and Typhoon test. So Typhoon offers a fully integrated tool chain, so from control prototyping environment to test automation framework. The whole tool chain is vertically integrated, so there are no third-party tools or licenses, and it's designed for control product lifecycle support. Okay, so for our setup today, we are going to have a real-time simulator, and then we're going to simulate a simple EV powertrain. So we are going to have a battery, an inverter, and a JMAG-RT based motor model. So we're actually not going to have an actual controller for the demo, rather the controller will also be implemented and will be running on the HIL device. So for today, we only have a PC and the HIL device. The PC is used to control the simulation flow and to execute the automated tests, while the actual simulations are going to run on the control on the HIL. So first, just a few words about the real-time platform or the real-time simulator. So it's going to be a HIL404. It's a fourth generation Typhoon's device. It's an FPGA-based simulator. It's got a very powerful FPGA board inside, which allows it to reach low simulation time steps. And in addition to that, the digital inputs that control the switches in the simulation are sampled every 3.5 nanoseconds, and this allows us to reach high switching frequency. Now, besides the FPGA, there is also a general purpose CPU inside with up to 3 user programmable cores, which can be used to simulate some slower processes like control, where we don't need such low time steps. So like some control processes, some mechanical, thermal, and so on. Now, if we need to simulate larger systems, there's a possibility to connect several HIL404s together so they can act as one big simulator. So that way we don't sacrifice performance, like increasing the time steps and so on for simulating larger systems. And finally, 404 can talk different communication protocols like Ethernet, CAN, or RS-232. So yeah, I'll quickly just go through the system architecture. So as we've said, we can view the HIL404 as 2 separate real-time simulators. So one is FPGA based and the other one is CPU based. The FPGA one is actually built for power electronic systems and for drives, and it's really application specific. So it's not a general real-time simulator. It really focuses on power electronics, drives, microgrids, and similar, while the user CPU is actually there under full control of the user, and it can be used to simulate whatever the user can make of it. Yeah, but it's intended, as we've said, for some slower processes. Now we'll move on to the schematic editor. So I'll say a few words about the system that we are going to simulate today. So we have the power stage here in black. So we have the battery, the inverter with the thermal model, and we have the machine, PMSM, which is actually going to use JMAG-RT model to parameterize our machine. Yeah. So we have two contactors here, one to simulate the phase loss and the other one to simulate short circuit between phases B and C. We have a simple mechanical model, and we also have the controller that's running on the CPU. Now, Typhoon HIL supports many different machine models, like most typical induction machines, PMSMs, one rotor machines, synchronous machines, DC machines, and so on. But it also allows direct import from JMAG-RT for the PMSMs. In addition to that, we have built-in position and speed feedback, so like incremental encoder, sine, cosine, protocol encoder, interfaces, and the resolver. And finally, since we've already mentioned JMAG-RT, now in order to support the JMAG-RT models, we need to also be able to support saturation and spatial harmonics. And where does this come into play? So these high fidelity models, well, it's so we can see the performance of our system. So for example, we have here a torque step response for the same machine, but with different with different levels of abstraction. So in red, we have the constant parameter machine, so constant inductances. In green, we have only saturation of the fluxes in the machine, and in blue, we have the spatial harmonics, which also consider geometry of the machine. And now we can see that when we do a torque step response, to achieve the same torque, we would actually need some more current in the more detailed models compared to the constant parameter models. And the spatial harmonic models also include the oscillations that come from the machine geometry. Now, the inverter model is also relatively detailed, so it includes forward voltage drop and on-state resistance, switching and conduction losses, and the thermal model, and also switching delay time. Now, to actually control the flow of the simulation, we use the HIL SCADA. So this is an interactive tool that allows you to control inputs to the simulations, set disturbances, and so on. So I'll just move to the first schematic editor to see our system. So we just need to parameterize the machine. We just set the path to the RTT file. This particular RTT file was downloaded from the JMAG example models, which is the accuracy type. So for today, we're going to have the LDLQ model, so we'll consider only the saturation. Here, the phase loss is simulated with this contactor. Similarly, the short circuit with this one. The inverter characteristics are imported using XML files that are obtained from semiconductor manufacturers. And finally, the control is running on the CPU. So I have the model already compiled and loaded into HIL SCADA, where I have my my control environment. So I'll start the simulation, and just to see how this looks like. So I'll maybe capture some signals, set the speed reference to 1000 RPM, and what we see happen here. So because we've got very low load, so almost only 3 Newton meters, we can see that while the machine sped up, we had some high currents to get the desired torque. And once we reach the desired speed, then yeah, these go back to zero. Now I can maybe give some step torque load, and we can see how our system reacts. So up until here, we had some we had some low currents with low load, and then this is where we applied the step, and we can see, you know, how our control reacts. So we can see that our speed dropped for a bit, but then, you know, everything went back to the reference. Now we can do with some fault injection. So, for example, we can see what happens when we inject phase loss in phase A, for example. Now we can see that up until here, all the currents are there, but at this point, yeah, because we we lost the phase A, then the phase A current goes to zero, and we got some very you know, disturbing signals. So we have very high oscillation in the torque. We got high oscillation in the machine speed. So I'll go back to normal operation, and maybe we can also do the fault in the IGBT in phase B. So let's see what happens here. And again, we can see something similar. So here are the currents. Once we apply the fault, the current in phase B is only negative, and we can again see some high oscillations in the torque, and we can see oscillations in the mechanical speed. Now this can be, you know, all of this can be then used to build to evaluate the performance of our controller. And what's nice about these, for example, all these widgets, is there is some Python code behind them, and this Python code can actually be used in the next step of the process, which is automatic testing. So I'll stop the simulation here because we're slowly running out of time, and I'll move on with the presentation and then with the testing. So our next thing that we're going to talk about is the Typhoon test framework. So Typhoon test allows us to create tests, run them, and get out-of-the-box reports. It's based on Python and open source projects, and it also includes graphical tools for easy test creation and running. So we can run these tests either locally or in a continuous integration process with a continuous integration server like Jenkins, for example. Now, it offers, since it's a part of the Typhoon software package, it offers native support for implementation of test-driven development processes. And now, Typhoon test is basically based on two large parts. So the first one is PyTest, which is used to execute tests. And PyTest is basically extensively used in software development, and it is the most flexible and complete Python testing framework. Now, it's mainly used in software development, but what we've done is we've added on top of it some electrical power specific analysis functions, like, you know, reference frame transformations, maybe analysis of frequency content, asserting whether the waveform of a signal is a step, ramp, or something similar. So we try to make it easier and more intuitive for use for power applications. And on top of that, we've built a graphical user interface to ease creating of the tests. So here is the actual test script, and on the sides here we can see what test cases we have in the script, which we have selected for the running, and and we can see here on the bottom right the log of the test. And finally, we have Allure as an open source, as a second part of our Typhoon test framework. And it's an open source reporting framework, which provides graphs, trends, interactive reports, and plugins to continuous integration tools. And it automatically logs every step of our test. So this is an example report, which I'll show shortly. So here I'll just switch to Typhoon test. And yeah, while this loads, I have the test report of my test already open. So I actually there were 8 test cases from 2 tests performed on our example system. So 6 passed and 2 failed. Now this is the test script. So we have 2 tests defined here. One just checks if the machine reaches the desired speed in 4 points, and the other checks if our performance during a torque step load change is as specified. Now this is the complete test script, so under 100 lines of code, and there is no code that refers to the report generation, so it comes automatically after the test is executed. So I'll just show here. So we are interested right in the tests that fail, and I'm going to jump right away to them. So the first one is number 7. So this is the torque step response. So on the right here we can see the log of the test. We can see what happens. So we set the speed reference to 600 RPM. We set the capture widget. We set some inputs to the simulation. We can see the capture results. So how our speed reacted, how our electrical torque reacted. And we can see now, check our assertions. So we had 2 requirements for our torque step response to see if the torque step is actually a step within the given boundaries, and this was indeed the case here. And we had another one, is that we don't want the speed to deviate during a torque step change more than the pre-specified, more than is pre-specified. And we can see that once the torque step is applied, our speed drops to below outside of the boundary, and that's why we mark the test as failed. So what we can do now is maybe review our system, maybe review our control algorithm to see what we can do to improve. And the good thing about this is that this test stays for us with us forever, basically. Maybe we can reuse it, once we readjust the control parameters, for example, or we can use it in other projects and so on. So yeah, with this, I'd like to thank you for listening. Hope you had a good time.
Okay, so thank you for the presentation. So feel free to ask your question. You can ask it directly in the Zoom application or in the UVA panel. So we've got one first question. What about the temperature dependency of the motor, and what about the demagnetization? I think this question has been asked when you presented the default, introduction of default, of failure, or yeah, default.
Okay. Oh, sorry. Just okay. So yes. So we are actually working on implementing this. So the temperature or the thermal model for the JMAG-RT machines is not yet supported, but we expect it to be relatively soon. So we're actually working on it, and yeah, I can't really say when it's going to be out, but yeah, we have all the frameworks or all the details pretty much sorted out. So yeah.
Okay.
Okay.
Okay. Thank you. Another question. Congratulations for the presentation. Did this example have a real implementation? If so, was the performance similar to HILS?
Okay, so I'm not sure. So we had some similar. We had some similar systems to this one, maybe not exactly like the one we have here. So maybe we had some more, let's say, generic motor drives that are grid connected. So we'd have a rectifier and a desealing stage here, and we've used both the PMSM and induction motors. And in this case, yeah, I mean. What am I going to say? The performance was quite close to the actual systems, and actually, we could also really tune the gains from the simulation to the controllers, and we were also able to really simulate in some cases some small errors in the current sensors, for example. So what we did is basically we could see that if there is a small error in the current sensor, then when you reach the limits of your drive's performance, then you can easily have a trip that occurs. And we were really able to reproduce that type of behavior on the hills as well. So yeah, that's one thing that I found really interesting there.
Okay, thank you. So yeah, feel free to ask any other question. No more question from the audience at the moment. So maybe I can ask you one question. Is there any limitation using the model provided by JMAG-RT? I mean, for example, I don't know, inductor or something like that.
Okay. So you mean in terms of the available component models, or specifically related to a PMSM?
Yeah, first about the different model available, like linear solenoid, linear motor, SR motor, something like that. And also, yeah, in the second way is also interesting as well.
Okay, so yeah, first, at the moment, the only available component model is the PMSM, basically. Okay. So we've had some feedback that it's basically the most used model, and we are really trying to nail it down there, with all the effects, like the spatial harmonics, which we're actually in the process of validating with JMAG. Then also with the thermal effects that were already asked. And then I think from there we'll then move on to the other models. And with regards to the second question, so yes, well, as I mentioned, so we have internal support for flux integral models, but we are still validating this with JMAG, so we need their approval to let it out officially. But this is something that we're actively working on, and we expect it to be very soon. And now in terms of performance, so since this is running on the actual hardware, so this is not an offline simulation, the most, yeah, basically the only restriction here is the memory size available for the lookup tables, because the RT files are essentially lookup tables for the torque, for the fluxes, or for whatever. So with real-time simulations, what you typically need to do is downsample these RT models further in a way. Yeah.
Okay, understood. Thank you. Okay. Maybe we can wait for 5 to 10 seconds to see if there is any question in the audience. Okay, and maybe in the meantime, I will show the next presentation.
Mm-hmm.
So thank you